Hello, everybody. It's me and Hendrik again. So last time we talked about neural Turing machines, or the article we talked about was about neural Turing machines. But today we're going to look at the article called Hybrid Computing using a neural network with dynamic external memory. It's basically from the same people, but the next step forward. So this came out in 2016, whilst the neural Turing machine paper was in, I think, 2014 or something like that. So since this is I guess this is a disclaimer or something. This is an article from Nature. So if you want to read it, the DOI is up here. You should see my cursor. So we're not going to be going through the paper like we did last time. We just snipped out the figures, and if there's some specific quote you want to see, then we're gonna quote it. But yeah, we're just going to. This is like you can think of it. This is like a slideshow, but on Google Docs. But if you want to read it, if this seems interesting to you, of course, go read it on Nature, and you can find it quite easily on that. But yeah, so basically, this is like a better written version of the last paper, which with some specific new differences between the neural Turing machine. Actually, now that I think about it, I think it's most interesting to actually start with what are the differences between this computing mechanism compared to the neural Turing machine. And the differences come down to how it writes and reads. So if you've listened to our last, I don't know, how do we call it, podcast or video thingy, our last thingy. So this is our second thingy. Then basically it had, if it wanted to read or write, it had content-based addressing and location-based addressing. So basically looking up something based on its content or based on its location. And so I'm gonna quote a few things from the paper, if I can get my copy to work. Okay, I'm gonna use it like this. So this is from the paper in the appendix.
Yeah.
Did you find it, Hendrik?
Yeah, I also was gonna point to the same part. From.
Yeah. Okay. So yeah.
Yeah, I'll chip in for a while also. So to me it seemed that that part of let's say the memory access part, which seems to be the main difference, is quite different. And these codes don't talk about it much, but it also involves this from a more technical point, which we will get to this, a matrix that designates what info is where, basically. So if before we had, let's say, a very kind of memory address-like thing, which is similar to how you would represent, let's say, a matrix or a word or something like that in memory, where you have, let's say, a pointer, and then everything comes after that until some time. But now it's quite different. It's to me it seems it's like you have, let's say, single locations, and then you have some kind of a matrix that tells you where something is.
Yeah, I think also all of these are big changes. So basically, it's a completely different architecture in some sense. But I think I didn't really think about this before, but it makes sense that this neural network can actually free up memory. So when it sees that some location hasn't been used for a while, it has some specific gates for it, some mechanisms, then it can basically reuse that memory location for new information. I don't know. It seems very logical. So I don't know how. I guess we missed that they didn't have a way to do it before, but yeah, it's interesting. Or do you think? I didn't think about it specifically before.
Yeah, and it also with the like, to me, although this one is different, but to me it also seems not like not only just better, but also different.
Yeah.
So the other one also has some very interesting logic behind it, and which comes to the third point, which is that like, how is the sequential information preserved?
So now they have a mechanism that they can just basically iterate back, specifically to iterate backwards and forwards from a memory location. Before they didn't specifically have that.
Yes, and what the backwards and forward means is very important. So they have this temporal link matrix, which basically tells you can put stuff in different locations, but still hold the information that this info is consecutive or sequential, actually.
Yeah, so they can very optimally use the entire memory, basically. Because otherwise you'd have to like redo the memory every time if you don't have this. You have to like. So
I think we say very optimally, but this is like every memory access is a cache miss. Like if you imagine you have like a huge memory, then everything is like random in some way randomly placed. So it's probably not like super computationally optimal end of the day to create these matrices and maintain these matrices. But for some size of memory, it's probably pretty optimal.
Actually, they talked about the complexity of the link matrices as well, and because they basically have you have a matrix where for each memory location, so you have a n by n memory n by n matrix that links all the memory locations together. And they have a way of basic, because then the more memory you have, the bigger the matrix. It like grows by the square. So I've always had trouble with complexity here. Anyway, it grows in dimensions very fast, basically, and but they can optimize it so the computational cost goes down a lot to log or just linear, depending.
Yeah, mostly I think because it's a very sparse matrix.
Yeah.
So you don't have to do the let's say there aren't very many connections in this temporal link matrix, but it holds things from important stuff, basically.
Yeah, and they actually make it even sparser by introducing this variable k, which has I don't know if there's a term in English as well, but in Estonia we call it Tambov constant. So it's they found out that basically if you it's a heuristic, basically. If you delete all the values that are below some value, which I think was 1/8, then you make all of those 0, then you can basically create a very nice sparse matrix. Yeah, and use save a lot on memory.
Yeah, and basically cool thing, but also is in some way it's also weirdly unoptimized, because let's say you if you want to actually load in some kind of a block of memory, then on a computer it is like stuff is usually placed sequentially and you load it in once. You only need the pointer to the first thing, not you need to load in every pointer and handle all of them separately. So if your computer has stored the matrix, you know what the start location is and what the end location is, and that's it. So you only need to give that information and then move that information around instead of yeah. So you have some kind of object. The object has some kind of a size, and then you can basically move raw pointers around theoretically. Bad practice in programming, but theoretically, let's say you can do low-level pointers like that. Here, it's like it's different. Like the old architectures was kind of like that in some way, but not quite. But this one is better in this application, but also most likely in the future they would probably want to expand on this memory access thing even more and making even more complicated structures for this memory access.
Yeah, because I mean, memory access system, I guess, is the main thing that makes this I mean, memory access is the main novel thing besides adding memory to a neural Turing machine. The neural network, how you actually access the memory, I think is the main gist of getting these things working.
Yes. But at the same time, they are most likely not computationally limited with the sizes of memories that they are using for these tasks that they're doing. So they aren't loading in Wikipedia to the memory.
Yeah, and actually that is also, if we just look at what they're planning on continuing with it, it was also the where is the quote? Finding it. Okay, never mind. But anyway, yeah, they have a lot of ideas on how to continue and move forward with neural Turing machines.
There is like to tackle real world data.
Oh yeah, that was the thing I was thinking of. Can you copy it here?
I'll try. Having some technical difficulties.
Yeah. So okay, to tackle real-world data, we will need to scale up to thousands of millions of locations, at which point the memory will be able to store. Wait, so they're basically talking about here is that why do you need memory? So like Henrik said last time, basically is that in a sense that the weights we currently the weights that neural networks have are basically kind of memory, but the issue there is that the memory is remembering like this broad information, but it can't remember like these variables very well. So for example, the example that they talked about was that okay, the neural network knows that a room can have chairs, but that doesn't make sense for it to remember like where in what coordinates the room is at, at what coordinates the chair is at in the room. But if you have memory into the system, then the neural network can actually like remember where specifically the chair is at. And so there are like different use cases for memory.
Yep.
And still, I guess one thing I would still like someone, maybe they're already doing this, but before we get to the paper, that they extend that the memory access has a penalty. So I would like to see like a hierarchical memory architecture, because it always takes extra cycles. If the neural network always presumes that it can basically get memory really easily, then it's not really optimal for, I think, large scale.
Yes, but to me that already seems something that you need to solve together with the hardware. So it's
yes.
Like you have like a specialized hardware and you integrate these different hierarchical levels to the hardware.
But I guess for me, like, yeah, but like, you can have specialized hardware, but I'm currently still thinking of like if you basically, so I don't know, so this will like this interference will be running, I guess, on a CPU, right? Then yeah, because all the memory, I guess it will basically have access to RAM and an SSD, basically. So what would it store in RAM and what would it store in an SSD?
That is an interesting question. Did they train it on RAM or VRAM?
But I mean, they trained it on GPU, right? Mostly. I mean, they talked about training a bit.
But
On a server where there were CPUs were workers, something.
Yeah, but I think the wasn't it analogy?
This is optimization. All networks were trained using a single version. This is just dump SGD. But I mean, it doesn't matter how they trained it because they didn't have any penalty, so they just had like infinite access time. So I don't think it specifically matters where the.
Yeah, I'm just wondering where are they actually holding the memory?
It's still in the architecture, so it's all in, I guess, all in VRAM.
Yeah,
right?
I think so too. Yes.
I think these are okay, not NVIDIA A100s because this was a while back, but still. So that is not really doesn't really scale down to, because that is the issue I run into with super resolution, is that you need a lot of VRAM. So it's always interesting to it's always funny to see like watching videos on new GPUs, like, oh, why do we need so much VRAM on like consumer cards? But as trying to do machine learning, then it's like, oh yeah, I want like a lot of VRAM on consumer cards because the professional cards are so expensive.
Yeah, and even if you have, let's say, half professional, like these business ones, then they still aren't usually the ones that have still a lot of VRAM. Only the computing series things like the A100s and stuff like that have a lot.
There was actually an interesting card that came out, like, I don't know how many years ago. Now it was 5, 6, 7 years ago from AMD. It was basically a workstation card that had like a 400 gigabyte SSD attached to it. So anyway, but actually, just before I go one more off topic thing is like interesting. How does, because now we have the I think with DirectX 12 with the new consoles, you have the basically the GPU can access. Yeah, I have this. What I don't know how they call it. Fast lane, direct like memory access, kind of from the GPU to the, I don't know, was it RAM or something? So
yeah, so yeah, basically, how do you load stuff into VRAM still?
Yeah.
Yeah.
I was wondering, but from where?
I think from CPU RAM makes the most sense to me.
Just wondering if I haven't looked into this. Just wondering if anyone's used that to like help like give more VRAM to GPUs in a sense.
Yeah, but still, it is still a bit slow. And
yeah, of course.
You do end of the day, it is probably, let's say, a couple of order of magnitude faster, but it's still like, as far as I've heard about GPU programming, most of the thing that is hard is moving memory and handling memory and making sure you have the data in memory when you calculate and optimizing the amount of time you can calculate. So it's basically like a memory handling problem. So even if you solve this thing in this neural network and you have, let's say, a CPU somewhere, then still you need some kind of like a memory handling thing. Which might not be something that the neural network needs to figure out itself, but it's still a problem, right? Of how can you access and use memory? Because in these, at that level of computer architecture, the prediction of memory usage becomes really important. So you can't say that the neural network can't ask like, oh, by the way, now I wanted for you to load me in some memory from the CPU to my GPU so I can use it while doing the calculation. Then it would be super slow. So, so it's an interesting question of how one would do that interface also. So some interesting questions that came up to me. Because this was, as you commented at the start, this, in my opinion, this was a much better paper than the last publication.
Yes.
And it so like the things that I thought about were more creative thanks to that. And also we had gone through the other paper, so this one was like a very similar to the previous one.
Yeah. So actually, I was thinking, like, was the other one actually published anywhere besides arXiv?
Maybe not. Or at least we. No, yes, there was. There was this. Remember, I also linked that in-depth one.
Ah, okay. It was a conference, I think, right?
Yeah, it was. There was also. Yeah, that one was a conference one.
I don't. No, no. The conference one, the more in-depth one, was for the one we didn't record for the spline theory.
Ah, okay, yeah, that was it. Got that memory.
So we need neural link and neural memory.
Yeah.
Okay, so I guess we can finally start with the actual paper, besides talking about our thoughts about anyway. So they actually renamed it now, so they're not calling it a neural Turing machine anymore. They're now calling it a differentiable neural computer. I like the neural Turing machine name better, but I mean, it's their idea, so like, they can name it what they want, I guess.
Yeah, but it seems like every time they make an improvement or change to the algorithm, they will call it a new name. But it is just unfortunate that they started with a very cool one. Yeah. And hopefully, if somebody figures out, yes, this thing now is quote unquote ready, then you name it back. You name it once again into a neural Turing. You make it like a improved neural Turing machine or whatever. So it would be like V1.
Extended.
Unfiltered. Yeah, unscented. Anyways, because I also don't think this architecture is quote unquote ready. But with this paper, they basically made a significant improvement. This one also basically open sourced the code.
Finally, thanks for them.
Yes. And they basically demonstrate the main gist of it is DNC is better than neural Turing machines, and it is better than other stuff that they're comparing to, and it is solving complex problems that other similar algorithms are unable to solve. Once again, they compare to LSTM as the conventional baseline of similar architectures, or basically architectures with memory.
Yeah, that actually was a funny quote. It said like it's better than everything, and then it said and it's better than LSTM, which is like, if it's already better than anything, then it makes sense that it's better than LSTM.
Yeah.
So this time they actually had the exercises they did were a bit more interesting. I guess as a preview to what we're going to talk about. So last time we looked at basically copying, and what else? It was copying once, copying multiple times. Yeah. As like associations, basically giving it an array, saying and then inputting element number 5 as an input and trying to get element 6 out of it.
Yeah. Basically, very, very toy problems that you would be able to solve with a conventional, let's say, program with a few programming lines if you were the one programming it.
Yes, yes, exactly.
Basically, that was that. But now the problems are, in my opinion, not necessarily also stuff that you can't do, can't program, but a lot more difficult to program.
Yeah. So the main takeaway from last time was it was like it was a lot better at generalization. So if it was, let's say, trained to copy 10 times, and then in test time asked it to copy 20 times, then it did quite well compared to like the next best thing, which was long short-term memory. But yeah, I guess we can start with how the network works this time. If I zoom in, does it zoom in on the web page as well?
Yes.
Okay. I think this is a cool view. So still, basically, as a controller, the controller can be any neural network type that you wish. This is a long short-term memory. The controller that controls the read and write heads is a long short-term memory controller, and it has the write head and it has multiple read heads. Basically, they're accessing the whole. So it's accessing memory. And it accesses the whole memory together, and this is so it outputs a matrix based on the last time steps and the current time step. They do the accessing different ways. So basically, writing happens such that you first erase a part of whatever you want to, whatever memory region you're specifically accessing, and then you write new information on top of that. And for the read gates, you can do location-based addressing. So basically, you can look up something based on a key. So basically, you have an output from the controller network and tries to match it based on some kind of distance measurement. They use the cosine, the distance. So basically a dot product, and then you can find the most appropriate answer from the memory, and then you can basically read out locations moving forward or backwards in order they were written in. So they don't have to be specifically sequential inside the memory. They can be. So we talked about this link matrix. So all of this will be depending on when they were written or written to, then there's this matrix that chains together these different memory regions. As you can see in the part D, so basically you have basically it's like pointers that says that okay, from this memory point, the next actual user memory point is not the next one, but I don't know, at some other point. And so you have like this array information embedded inside the memory itself. Did I miss anything? Most likely.
I think not. I think like the pretty good figure to explain this further is this figure 3.
Okay, that's a figure.
I think that, yeah.
Okay.
Well, maybe not explain, but has at least a visualization of how these write heads, read heads work together, and and the read heads being in different modes. So there is like these 3 parts. The first part being the graph definition part, where basically the graph is being made. Then there is like a query given, where it's basically a question asked. So this was or maybe we want to explain this problem a bit further before we get to the answer. Actually, because I start thinking about it, might be a bit of out of place, but this maybe we want to, or no, let's continue with it a bit, but then come back to it so we can explain it a bit further in the but still you can here see the different read heads behaving very differently in different let's say modes, where you can see very specifically read head 1 when it's a query mode, being able to read using this content quantum framework, and then the readhead 2 being all over the place. And when it's like this answer phase, then the readhead 2 is basically in the content phase, basically providing this direct access to memory, basically. So it was a very interesting illustration of and like visualization of basically these different memory, like the memory access quite straightforwardly. When it's a query reading and when it's like an answer from the neural network, once again reading from the other readhead. So it was quite interesting to see a visualization of that. At least that's what I got from it. Did you get the same?
It's for me. It's always a bit difficult to understand this these specific graphs, even in the last paper as well. But it kind of when you talk about it, it's a bit easier to understand. But
I think, but I can't.
I guess the only question for me is what does this mean? That so I guess when the readhead 2 is reading this, let's say content based randomly, right? What is readhead 1 doing? Is it still reading in diagonal? Is it still like reading in? What's it reading in? It's like reading questions. I guess it's reading right. Readhead 1 is reading in the question. Oh, and readhead 2 is finding the answer, or.
Well, so the problem statement is that so the query is getting from one like so first like so let's describe the problem. So this is figure 2 is kind of middle thing, but actually it's maybe so let's go to, so one of the problems that they had was so we thought that there was more realistic problems. One category of problems is everything graph-based and solving graph-based problems. So finding the shortest path was one of them. And basically this problem that we started explaining below was this finding the shortest path type of problem.
And so it's so one of the examples for the shortest path was the London Underground. So basically they gave as inputs, they gave triplets. So basically how to get from Oxford Circus, if you look at the very first input, how to get from Oxford Circus to Tottenham. If let's see, it doesn't get that much better. I don't see it. Basically, it says that if you want to get from Oxford Circus to Tottenham, you have to use the central line. Is this like one? Is it the question I have? Is it one stop? Yeah, it's one stop. So all of this should be like one stop.
Yeah. So basically, you have so it's like each one stop. So if you put all of these links in, you get a graph, basically.
Yeah, like on the left side. So.
Yeah. And now you can basically you populate this graph, and then you ask, how can I get from one place that is not connected to another place the quickest, basically, and what? Yeah.
Yeah. So basically, so for this underground station example, all the names are the nodes. So if you don't know about graphs, so the nodes are the circles here, and then between two nodes there are edges, and you can see there are arrows on the edges. So basically this shows whether, in this case, you can see if they can basically move both ways through this one edge. Is it unidirectional or is it bidirectional? And the edges are then the names of the specific underground lines. So if this is Oxford Circus, for example, and this is Tottenham, then through the central line or central edge, they can move back and forth, basically.
Yeah. And in the middle, you see there's this shortest path question of if I want to. So on the right one, it's the shortest path. On the left one, it's a traversal. So if I want to get from one place to another using some method, some specific lines, basically specific type of edges, then it will give you an answer for that. Basically, what would be the
So it's basically the same thing when you're looking at how to get from point A to point B, and you're trying to look at the shortest path, which I think is the more useful one. I don't know why would you use the traversal.
Not that familiar with the problem, but because I deal with robotics, so shortest path, best problem.
Yeah. And then when we get into this with what we were talking about before, then first it gets in these triplets. So basically, how you get so no, these are decoded. Also, these are decoded memory allocations.
I think the colors are let's say what type of what type is. So yeah, so the bottom ones.
Central.
Yeah.
Okay.
So the bottom ones there are basically the colors, and that's like the what type of line is it, or like no, what kind of, you know, the what train takes you from or what
line.
what line takes you from what line, you know.
So the first part here is basically it's reading in the information. So this is already, I guess, test time, not training time anymore. So it gets this information in about how the graph. So this is basically it gets in the graph. This is the graph. So it gets all the information in how the different stops are connected to each other, and it creates this similar kind of looking graph. And then it starts getting in the questions. So it asks how do you get from. So I don't know if these are traversal questions.
Mm-hmm.
So if you start with, basically, if you start with Victoria and you go Victoria North, so where do you end up in? I think is the question, right?
Yeah, I think so.
So the answer should be should come to Green Park. Yeah, so you can see it looks up. The question is this one, and it looks up content based. It looks up Victoria. The next one is Green Park, if I understand this correctly. And then the next question comes in. It's still writing the questions into memory, but it's not answering them anymore at this point, right? It's just or what's happening?
Well, first you query it in, and then you answer. So it's not like it like.
But why is it reading
in the whole query? Huh?
But why is it already? Why is it like finding the answer for one of the queries and then? Or am I misunderstanding something?
Good question. Don't know, but probably it is able to understand that this is the. To me, it seems like it is reads that this is the start station during the query. Like it has a question and it connects it in memory to this is the start station. And this is relevant to the query, so it is part of the query basically. And then it is, and then there is the answer phase where it is outputting the whole, let's say, path then basically for the different connections.
Yeah. So it's just weird. It's basically do the same thing, more optimally if it started answering right away, right?
Well, they're.
They're just losing time. It's a traversal question. It's a traversal question specifically.
Well, maybe with this problem theoretically, I'm not sure. I don't know enough about the traversal problem. Do you need to optimize something here or not? But let's say it's not a traversal question. Let's say it's a shortest path question. Where you need to find all of them. You need to find the shortest path, then you don't try to answer right away with what is the step you want to take. So maybe, but maybe architecture-wise, it is like setting it up as a query and answer. Because let's say,
My only opposition to that is that it was specifically trained for a traverse. This one was specifically trained for a traversal one. Of course, it still accomplishes its task, as we can see. Because as you can see also, it starts right. It reads in the first. So basically, it starts with reading in the second query, and it starts with answering the second one. So it doesn't re-answer the first one. So it remembers the answer for the first one here somehow. And it goes, because it knows it says Green Park. From Green Park, it goes to Oxford Circus. Then it goes to...
So basically, it processes the whole query, and then it processes the whole answer still. It's just but the answer there, it's a part of the query. Yeah, knowing where you start is part of the query, not part of the answer, in my opinion.
But yeah, anyways, it's goes through.
I will ask you a question: how to get from one place to another? Then to be the starting location is part of the query. Where do you, basically you ask somebody a question? I want to get from A to B to C to D, but like if you start answering that problem, then you need to the starting from A is part of the question. So basically, if you look at the traversal graph, the Victoria on the left there is that query, or is basically now part. So if you put if you fix more parts of this graph, I think they would also be queried, and you would see more red dots in the query part, basically.
Okay, I get it, but I'm just thinking like how I would do it. I would start like I didn't care about. I just start with the first one, which is Victoria to somewhere by Victoria. Okay, look, it goes to Green Park, and then you automatically it goes Green Park to the next one, and you can go step by step. I don't have to go look for all of this, right? To start answering. You can start answering right after the first one.
I mean, this question also seems very trivial, but let's say you have multiple paths that you can take still, and you would have queries where, okay, you have multiple paths, but some things fix points in the middle. So imagine it under the Piccadilly, you have one of these points fixed where you need to be, or you could even say that these Piccadilly ones are fixed points. So that's why they are queried there in the bottom also. So, but still in the end, but they don't need to be queried from there, but still,
my point is that,
yeah, go.
That wasn't the exercise. Oh yes, I agree. If it was an exercise where, like, say in the center, like instead of giving the first answer, starting by Victoria, start with like at the center there is north. Then of course you still don't care about the ones that are after it, because you can do it, but you have to like read up until north, and so you can get the first part. I just say, I mean, it works in both ways. Just wondering why it doesn't need to wait until the end of the query to start answering this question. It could start answering right away.
If a middle point was fixed, then it would need to.
That's what, yeah, I agree, but that's not the exercise. I'm quite sure that the exercise, at least from this, it seems that every time that it starts from the first stop and it ends up somewhere.
Probably. I don't know enough about why propose a traversal question.
Yeah, most likely it's for it.
I mean, it depends on how you could. Yeah, because you could. Right now, the definitions are once again given. So, like the third one is not given, but once again the other, like the different things would be given and not given. And, but still, it will. I agree with your point that right now it seems only one iteration is always done, and there could be an output after each iteration. So it could be query answer, query answer, query answer, query answer, instead of big query, big answer.
Yes. So it's a solution. It's not. I just think it's not the optimal solution for this specific problem. And I know your contract argument is, what if it's a different problem? But it's not a different problem. It's this problem.
Okay, my point is this architecture generalizes, so you should solve the case.
I mean, you don't know if it generalizes.
Well,
you know, it has like it has a better chance of generalizing. I'll give you that, I guess.
Anyways, we can move on from semantics because it's the boring problem.
Yes, and then on the right side you can see basically the same kind of, let's say the same kind of problem, but just the shortest path for the same kind of, I guess, general problem. I don't know how. Anyways, trying to get from to somewhere. What is the shortest way to get there?
Maybe. Is it?
What?
I don't think. I think it's the same problem.
Is it?
No?
Wait. Ah, it's the whole thing is traversed on the underground. Yeah, my bad. Yeah. I don't know how I messed that up.
Figures, hard read.
Yeah. Okay. Before actually this, there was another problem. I know actually. No, there wasn't another problem. I'm misremembering.
Yeah,
the family tree.
Okay, that one.
It's the same idea. Just trying to find. So they're giving a family tree input, and they, as the ages this time, there's the relationship. So Alan is Charlotte's father, Steve is Simon's father, and so on. And then they ask inference question: who is Freya's maternal great uncle? So it's interesting how do they decode maternal great uncle?
Yeah, they just probably have, let's say, like, I mean, most of it is like a natural language processing task. But no, it's encoded in some obvious way, where it's like father of father, mother of father of mother of brother of something.
So then they find who is Freya's great maternal great uncle. One thing they didn't have a figure for is that they also had this synthetic question answering experiments. But I guess so these are a bit like related. But so basically they had like these kind of questions like where John is in the playground, John picked up the football, and then the question follows, where is the football? And then the network is supposed to answer playground. Or a question can be like, sheep are afraid of wolves, Gertrude is a sheep, mice are afraid of cats, what is Gertrude afraid of? So in this case, the mice are afraid of cats is like, it's just a distraction, and the answer should be still wolves, right? And what they said here is so this is a bit, so I'm going to copy it. I was a bit
I'm copying it already.
Okay, let's see what you.
I'm copying it.
I'm copying a bit more, so I'm going to recopy.
Okay.
So my issue with this question with this was if you understood that. So basically, they said that they used here basically just natural language. They didn't really do any. Did I copy the wrong thing?
You copied from the lower part.
So basically, just what the question is, they said here that they just didn't do any like processing on the questions themselves, right?
I think this kind of said they didn't. They were categorized into 3 categories of object, action, and whatever. Somewhere it was mentioned.
So that was afterwards the graph that you could easily be rendered in graphical form. So I think they did it. So yeah, so they didn't do it. So they could easily put this in graphs.
Okay.
John is in the playground, then you can put John and playground, and then connected with an age called contains. But they didn't do that. They just did it with the purely natural language, it seems. So each word was a token, so it was not character based, but word based. And then they got these quite good results with this.
And the cool part here is that I didn't copy enough. Anyways, the cool part here is that it is solving both inference questions and which is, but also like deduction questions, which is harder, in my opinion. Where was it mentioned? Even in the same paragraph. So the first part is, let's say you have how to pick up how to explain it well. If you know how to explain it well, you can take it over.
Why deduction is harder than inference?
Yeah, exactly.
I don't know. I was waiting for your answer to explain that to me.
No, okay. No, it's I don't know exactly. To me, it's like a very big intuitive difference if you compare the first set of facts and the second set of facts, and that would be. I would say that to me, the first one would be something that is easy to answer for a computer, while the second one difficult to answer for a computer.
So
fully intuition. So the first one, the John is in the playground. John picked up the football. Football, it is like a transfer of ownership. But the other one is like contextually, sheep are afraid of wolves. Gertrude is a sheep. Mice are afraid of cats. What is Gertrude afraid of? So it understands that the A is B, therefore B is C, or the A. Well, yeah. If A equals B and B equals C, then A equals C, basically.
Just one thing, not the off-topic thing to add, just for this is that this was based on the BABI dataset. Yeah. If anyone's interested, baby. But yeah, then it had one more type of problem they tried to solve, which was this basically this. So I tried to find. So I don't know how you pronounce it, but Shildlu, mini Shildlu. Tried to Google to see what is it. Some videos I didn't see any. It seemed all like some science videos. So it seems it's like some kind of toy problem, or problem for computer scientists. But basically, you have these kinds of blocks, and you can. The only thing you can do is take a block. So in this case, specific case, you have 3 columns and 3 rows. The only thing you can take for in each step, you can take one block from the very top of one row, from one column, I mean. So in the first one, you can either choose 4 or 6 or 2, and then move it to an open space on top of another column. So you can move 4 on top of 2, or you can move 2 on top of 4. These are the only 2 moves you can do in this very specific case. And then you have some kind of constraints or goal. So for example, this specific one, goal T. So they said that 6 has to be below 2, then 4 has to be left of 1, 5 has to be below 4, 6 has to be right of 3. So that's how the goals are encoded by these letters. And then it tries to get into the situation, and we can see that the 5 is below 4, 6 is below 2, 3 is right of 6, 6 is right of 3, and so on. So that is what it's trying to do. One thing I don't know is does 6 have to be immediately below 2, or can 2 and 1 like switch places? Of course, there's the constraint that 2 has to be below 1 as well, but I'm just thinking whether 2 can also be above. Can something be between 6 and 2 if you don't have the constraint 1, and that 1 has to be above 2?
Because the names are GTCA, then it seems like it's a toy problem for matching some kind of biology systems.
Oh yeah.
And it's like but I am not a biologist, so can't make the connection of well, what kind of what type of problem is it in real life. But it seems like a toy problem for some kind of genetic code reading thingy. But why and how, don't know.
And so there is so they have so one thing they show that they can do it, but one thing I didn't really understand was this D&E part of the figure. So the part D of the figure should show that on 800 random episodes, the first 5 actions that the network took for the chosen goal were decoded from memory using logistic regression at the time step after the goal was written. Decoding accuracy for the first action is 89% compared to 70% using action frequencies alone, indicating that the network has determined a plan at the time of writing many steps before the execution. Error bars represent 5 to 95 percentile bootstrapped confidence intervals on validation data. So I don't know if we can go step by step through this sentence or the statements or whatever. So they had like 800 different places.
It's like a prediction of so if you had you have the net predict 5 actions. Okay. And what is the accuracy that it predicts the future actions with? You can to me the analogy here would be a chess engine trying to make predictions about what moves it will make and then trying to evaluate the state where it is in 5 moves. To make the optimal decision now, you need to predict.
Okay. So basically, so the difference would be it makes 1 move, and it makes then based on the new state, it makes the second move compared to if it just looks at the beginning, what kind of moves it would actually make. So what's the difference between those 2 things?
Yeah, because with that is in like theoretically, if you have this, let's say, neural net and you have the previous state, right, and then you could basically, and then you predict basically the next state, and then so that you could then run the state again to predict the next state, right? So that's the advantage of this type of recurrent nets. You could basically do 1 more time step.
Yeah, so in this case, you're trading off latency for accuracy.
Yeah, but it also the fact that you are able to solve this problem like that at all, I think, is that you are able to do this. Basically, because what it needs to do is it needs to store this intermediary result into memory.
Yeah.
Between these action numbers, it needs to run the computation loop again, and then save the stuff to memory, and then let's say the actual new state comes in, and then it needs to do it again. Basically, take in the history and the predict once again the actions into the future in order to make the best move. Basically, because otherwise, just asking for the next best move without doing this, let's say, playing through the optimal moves is bad. But you might have too large a search space to just, you can't calculate all potential combinations, basically. So you do the best action, what follows the best action type of thing.
So, but what does specifically mean? The decoding accuracy for the first action is 89% compared to 17% using action frequencies alone. So,
the second part is confusing, right? Compared to action frequencies.
So if I understand the first part, then So
I think action frequencies is if you just action frequencies would be the best move is to do this action because it is the most likely action. Is that action frequencies? I think so. That's doing the most likely thing because it has been done before.
okay. So anyway, the main idea to get out of this is that basically the neural network actually creates a plan before starting the movements. So it doesn't just go like Henrik talked about going best move, best move, best move, but it actually has a plan on how to get from point A to E with the middle steps of BCD.
Yeah.
And so so basically they had rather 8 random states and they tried this. So E. So there was this T-distributed stochastic neighbor embedding. So T-distribution is basically, I might remember this completely wrong. When I got this definition, that was, I guess, the last time I learned statistics specifically was 8 years ago, something like that. Anyway, when I was in my first or second year of bachelor's, and if I remember the distribution, it was it like basic normal distribution, but if you have a lot less samples, then you have some kind of differences. Is that correct?
Something like that, yes.
So take our definition.
T-distribution is normal distribution, but your coefficients are
bigger.
Yeah, exactly. And there was some kind of reason like that.
As a very quick, we're from Scribber.com by Rebecca Bevans. The T-distribution, also known as the student T-distribution, is a way of describing data that followed a bell curve when plotted on a graph, with the greatest number of observations close to the mean and fewer observations into the false. It is a normal distribution used for smaller sample sizes, where the variance of the data is unknown. So the variance is unknown. So basically you have a lot less samples, and then I guess, so if you want to get like 95%, and you multiply it with a bigger number, is it?
Yes, but don't you also do that with normal if you want to find the coverage factor? Anyways, I remember when studying that and being like, yes, weird way of so it's like physics education backwards. Like half of the statistics stuff given is like you're thinking like, why are you using this thing when we have a better thing? Stop using the worst thing.
This brings back great memories of calculating the degrees of freedom.
Yes.
And you have this very so degrees of freedom means, I guess, can mean a lot of different things when you're doing like uncertainty calculations. Degrees of I don't remember the what is the definition of degree of freedom. It comes down from, I guess, basically, so there are different types of there are different types of errors, A, B, C, and for example, I think for the type A error, if I remember correctly, one error comes from the measurement. What are you measuring with? I think that is the type B error, and type A error is you're doing like 100 measurements, and you see what is the difference between those measurements, and if the difference is small, I think the degrees of freedom is bigger or smaller. So somehow from that you calculate the degrees of freedom, and then somehow you have this long equation to calculate the total degrees of freedom that your result has, and based on the degrees of freedom, you can calculate the actual coverage factor, or you can be a lazy. So that's how, when you start learning physics, that's what you at the beginning do. You are very meticulous, but after like 10 practices, you get lazy and you just say, I presume a normal distribution. You multiply the coverage by 2, and you say it's 95%.
Yeah, and realistically, if you or you have this heuristics with different number of samples, you go higher than 2. You do like this, and then you have, let's say, if you have
Lower number of samples, no?
Yeah, but then you have, if you have multiple normally distributed variables, then you get new cool equations right away. So
Yeah.
And then it actually is important once again.
Yeah.
But degrees of freedom versus dimensions, and then let's say we realistically learned the more complicated, intuitively more complicated thing first, because
it was, I think, the very first course in physics, and everyone was like, "What the fuck is going on?"
Yeah.
But can you now, after this small tangent, can you now tell me what figure E actually tells us?
So it's like de-distributed stochastic neighbor embedding sounds like we are looking at the we are trying to separate classes based on their dimension, like their distance from each other, and we are trying to separate them into classes based on let's say like some distance metric between these others, between other classes.
But what are the labels? Like, because we had only like R before. Like, what are these labels?
So why is the image like that? Why are there X and W's and Z's and whatever?
Yes.
Don't know.
Okay. Anyway,
it's a confusing image compared, because there are no mention of classes like that. But basically, the goal here is to group elements into categories and then give them a common.
So basically, it's they reduce it down to 2 dimensions. So they're basically trying to find the underlying, I guess, manifolds.
Yeah.
And what they, or not even the manifold or whatever, the actual basis, theoretically.
Yeah.
Anyways, they separate nicely whatever these letters are, mostly nicely.
Wait, that shows that each goal label. So those are maybe goal labels, and so it's looking at it over. It's like maybe then looking at the space in memory, and then comparing the different. So it's like it shows that in memory,
the different goals are separated.
Yeah, over time. Maybe that would make a bit of sense. Still, I'm totally confused how it came in and what they actually did here. But maybe that's what they wanted to show with that image.
Okay, anyway, just so within trials, we average the location contents associated with each goal label. So across all the trials, it always put the same goal, similar goals in the same place, I guess. But then I guess that's also weird. Within trials we average the location contents associated with each goal into single vectors. Across trials, we create a data set of these vectors. So there are different trials, and the difference in each trial is just the hyperparameters. I guess the exercise is still the same, and it basically finds that it still puts it in most likely the same address points. Whatever.
Yes. So it's basically okay. That's actually quite interesting. What they are showing then is that the memory representation learns a very similar representation every time, which is cool.
It's kind of like reproducibility.
But it's also not only that it's reproducible, but it also probably means that this is somehow a good memory layout. So you could say that it is finding a layout that is so good that it always finds it.
Or it just means that it's a deterministic-ish.
But it doesn't make sense for it to be deterministic, right?
What I would think is that if the goals are the goals always at this? Do the goals always come in at the same in the same sequence, and it just always puts it in the
800 random episodes. The first 5 actions from the network to blah blah blah. 800 random episodes. What is an episode?
If you have one of your episodes. So I think the random. I mean, it's okay. So the goals cannot be random, otherwise this doesn't make sense at all, right? So the only thing that can be random, there are 2 things that can be random. Either the sequence of the goals can be random, in which case it would be more interesting. Why does it choose to put A in the same place every time? Or at some point it said like, I think the randomness is just the starting. The hyperparameters are the same, but just starting weight distributions. You take the weight, not the distributions, but values from the distribution.
After all of the goals were presented, a single goal label was chosen at random, and the agent was queued to satisfy the goal.
Yes, that is.
Figure 4BT.
Yeah, that is just that they gave it like a bunch of goals, and then they said now deal with goal T or whatever, basically. So they gave it the A to Z goals, and then they just picked one goal that it had to satisfy. So basically, giving it I don't know. Basically seeing if it can remember the goals, if it has multiple goals.
And of course, the 4E is not mentioned in the text. So it's a classic part of somebody was very impressed with the article and did not give review comments because they were very impressed. By the way, you're not mentioning this E part, and what the fuck is on the picture? Oh, sorry, we forgot to write about it. Somebody was editing figures and took the text out. Real life problems.
Okay. But anyways, it shows that I can do this, memorize different goals that it has, and then execute on one of them. So this, I guess, I mean, the amount of goals that it can remember is of course based on the memory size, which actually shows in the appendix as well that I put in this image in a different exercise, but still you can't go over the memory size. So this was basically just a traversal task, and it shows that how much it got correct also, of course, depends on what is the traversal size compared to what is your memory size. So it's also interesting that even if it's not fully optimal because it can't traverse the whole thing completely accurately, even with it has like exactly the same amount. So it needs a bit more memory to traverse, which makes sense, I think. A bit of overhead, but yeah, you can see. Yeah. So even if you have 500 memory locations, I don't know. So it's a bit difficult to understand actually. So even with 500 memory locations, you can't get like full accuracy. Or would be nice. I don't know how informative this is, like how accurate this like part of the upper diagonal is. It seems quite random. So if you're over this linear line, it seems quite random at some point, and how accurate you actually are.
Yeah, I also do not like data presentation.
But I think it's like these are like nice, cool figures for nature.
Yeah, it's like guys, I did an XY plot. Guys. And I put another axis which actually holds the information on the right and put colors on it. But actually it's a 1 and 0. The colors almost don't do anything because we're not tuned into the part where actual relevant info is. So it's like, and there are no numbers. So I don't understand shit from the plot. But it's a cool looking plot and you can see that it scales.
Yeah. Basically, maybe I don't know if a logarithmic scale would help, or maybe just having a different color map would help.
Or just make a figure and say like, and there isn't a picture, there is just like a text. This scales linearly with words, and then put that in if you.
Actually, I think a best way would be just to add like like a graph of accuracy, like with the percentage of memory allocations based on graph triples.
Yeah.
But anyway, let's not talk too
like
much.
this. No.
And then what? So this is also results for the same problem we saw before.
Yeah.
So they basically, so here they are comparing the differentiable neural computer compared to long short-term memory, and this is the same issue that they basically had in all of the different exercises, that LSTM basically can't get over less than 10. So they use the curriculum learning. So this is something we still have to get to. I don't know what it exactly is. Do you know, Hendrik? Do you have any definition?
Not before, but the quick Google said that it's a strategy for training in a way that things are generalizable, and the idea is that you first give in simple data and you go more complex. So
basically, so you can think of it as the first lesson is grade 1, lesson 2 is grade 2, and you go through until PhD. Each lesson gets harder. And
the idea is that you have to generalize basically. If you have, so it helps to generalize is the
goal.
Potential thing, and what some experimental results support basically.
I think it's quite a hot topic, and it's also something we're going to look at soon. We have like free paper. If there would be like many people watching us, we would do a poll what the next paper is. But since there is no one watching us, then we will choose ourselves. And anyways, we have three papers that we're thinking of doing next. One of them is about curriculum learning. The other two are basically the continuation of the same memory access issue that we're currently looking at. And but what this graph basically shows is that on the x-axis we have basically how much time it has to spend, the neural network has to spend on each of the lessons to, I guess, successfully learn it. I don't know how success is defined, but somehow it is defined. And then you can see most of the DNC networks go up pretty fast. Some of them, due to have random initialization, go up slower depending on the beginning parameters. But you can see that the LSTM, which is like before this, like the, let's say, the state of the art for these types of problems, I guess, gets stuck at some lessons. Usually, it was, I think, quite universal in all of the exercises that it didn't get like past lesson 10. It gets like stuck there, it doesn't pass successfully. So you can say it doesn't generalize as well, or it just doesn't have the it doesn't have enough memory to deal with these problems.
Yeah. Also cool. With this problem is also the extended data figure 3 is related with this.
Figure 3, I will put it in.
Yep. So I think here is a cool part of what that shows, in my opinion, the one thing is accuracy, but in my opinion, the cooler part is the generalization to multiple moves. You could say the ability to predict the future in some way. So the prediction mechanism of this DNC approach, it generalizes much better to prediction versus fitting to data, would be my conclusion based on this type of information. LSTM compared to DNC.
Yeah, it doesn't. Basically, at some point, I think LSTM just doesn't have enough places to store the, let's say, the thinking through on how to get to point F. Also, yeah. It doesn't work that. So as you can see, constraint doesn't really affect it. It's quite like steady, but it just decreases with the number of.
Yeah.
Actually, what was interesting is that constraints make it easier. The more constraints you have, the better it gets. Which is interesting. Yes, I wouldn't have thought about that. solution.
Yes, I also would that, but I also kind of know that LSTM has some weird failure case. I've heard about it, and I think that's kind of like shows a failure case of very. I think what happens is LSTM doesn't generalize well, basically. And if you give it more constraints, it has more data to make bad predictions.
I'm a bit confused. So you're still talking about the same thing, that the more constraints you have, I was like, then
it should make better, and in the DNC case, it does mostly make it better, and it should make it better. Yes, you can also see in some cases it doesn't, but I would say that's also weird.
So yeah, it's interesting. If you have one constraint, it's like coming not too bad. It gets worse, and it starts getting better.
Yeah.
Which is interesting.
Yeah, but it's also the minimum required moves 7 part, which is you have to predict many moves basically, which is also interesting. But this one was also not explained at all in text, so
like I said, this was like an appendix, so it's just like interesting.
Yeah. Well, but the numbers here are very important and interesting in my opinion, because let's say once again, I think that LSTM is like in my opinion, if somebody told me for many problems in robotics, choose a neural network architecture to use for this some problems that I am facing, then I would say LSTM would be my intuition. But there's also similar problems that but is it able to actually learn the model of the thing that you are trying to, let's say, use between these timestamps, and or does it overfit to some existing data that you have given it?
I guess that's everything is used by use cases.
Yeah. But it's like is the memory like is it like a parameter that you learn in memory there, or is it like, does it use memory as like now I have more memory to overfit my solution to?
I mean, that's the dream of every neural network, I think.
Yeah.
But yeah, and then if we continue back to the figure 5, which is also the last figure of the article, if we don't count the appendix. This basically shows how successful they are at each lesson. So it's either perfect, it does everything correctly. It's successful if it's based on some kind of percentage. I don't know exactly, but success is if it's correct at in some percentage, and then incomplete if it's not. I don't know if what are the numbers? I can look up. Okay, so basically success is if it's a success if it finds the optimal solution. That is perfect. Success is if that takes a few more moves than optimal solution, and failure is if it doesn't satisfy all constraints.
Yeah. So my first question would be, who the heck sorted the graph B, and what the heck?
What you mean? Because this is just the lessons.
It's lesson. Okay.
Okay. Which is interesting. You don't have like a steady decline in the perfect. You just have this a bit like jostling up and down.
Yeah. That was like, what the fuck? Okay.
I just wonder. Saying this without having any knowledge in curriculum learning, I'm wondering what the ideal graph for a curriculum learned, what would it ideally look like? Would it have like some kind of course it will have a decrease in the whatever success rate definition we have. But how would it ideally drop off?
But it's also a combination, so it's a it's at some points you generalize better, and that therefore achieve better success, because increasing complexity might force you to generalize better also. So it's not there is a decline because problems get worse, but it's like, once again, a school analogy is great. Sometimes some parts click and then you feel like, oh, I know this part and the old parts a lot better. So I feel like I know more about the topic, but then someone hits you in the face with some very bad equations.
So, I remember being in high school.
Green theory, or what was it?
Oh yeah. The green, the differential equations.
Yeah. I feel like you're getting better at solving different. And somebody hits you in the face with some fucking green bullshit. And like, no.
Yeah. I just remember every answer is the green equation. Don't know how, don't know why, but the answer is the green.
You can solve every problem. And then you go there and say, guys, I solve my differential equations numerically. Fuck you guys, I'm going home.
So most people most likely don't know what a green equation is, but when I was in high school, I remember very like a simple example was in maths we learned the geometrical sequences or geometrical series and I guess algebraic, was it linear series or algebraic series? A linear series, I guess. You know what I mean?
Not exactly.
Geometric series is like you have every time it's so linear series is every sequence is that every time you add a number to it basically, and geometric series is if it's multiplied by something every time.
Okay.
And then I was like in physics, and then we have the equation for acceleration. I was like, wow, this is a linear series. Anyway, we're mind blown. But so if we look at the discussion, if we go off that tangent, if we look at the discussion, so I'm just gonna copy a few of the quotes that I will do this actually here. And I'm gonna delete this.
I think one cool thing is that if it can solve graph-based problems, it can solve almost anything. Is discussion point number one. Well, actually that would be maybe my strong point, that if you can do graph-based stuff, then I would say it's one order of magnitude more applicable than what we were looking at last time.
Yeah, there's actually a lot of, if we talk about accelerators for deep learning or neural networks, then one of the big things people are looking for is basically graph machines or whatever. Basically, just how to do computations on graphs. So it's a very big research, I don't know, soon way.
And robotics is also where every second day somebody, oh, I have this new cool graph-based thing. Would you like this new algorithm? What is it? It's a graph-based thing. So that's why.
So graphs are cool. So if you want to become great, learn graphs, I guess.
Have a neural network. Make a neural network that solves graphs.
Hypergraphs. I mean, I guess if you for what reason you're listening to this, most likely you also listen to Lex Friedman podcast, which I suggest. If you don't, then I suggest you do. Then I think it was Wolfram, Stephen Wolfram, or someone. They were talking about hypergraphs and stuff. I think it was Stephen Wolfram talking about hypergraphs, and that in the end went a bit over my head because he basically started explaining how you get God and universe and everything.
Yeah, but Wolfram podcasts and there are very nice, very fun. How complexity emerges from simple rule-based systems.
There's actually a really cool book on it. It is called Complexity. It's basically based on the Santa Fe Institute. So Santa Fe Institute is also Wolfram was one of the first. Was a bit associated with the building of the Santa Fe Institute, dealing with the same kind of stuff. But what is complexity? Like how you have systems. There, what's the word? Positive feedback systems and negative feedback systems inside whatever system you have, and it creates all this kind of different cool things, very dynamical systems. Like before complexity theory, that day, when you talk about economics, they always talked about how you have these very smart actors, as what you think of humans, and they always make these optimal and good decisions, and then you have the whole economics from it. This is a close simplification, but basically.
It's of course a joke, but
and then the Santa Fe Institute, they started doing like basically put like basically heavy maths and ideas into it, and they have this like, of course, cellular automata. Some people worked on that, and then you have all these biological systems and like. But anyway, I'm not going to do a review of the book here. I suggest you read it, or if you're interested in like complexity and
when we are done with machine learning, then we'll take those topics on.
When
it's completed.
Then I guess we have to start doing a paper a day or an hour.
An hour, quicker. I think.
But these are the three things. So one thing was a graph. If you can work with graphs, then that's, I think, if you can feed into graphs into your neural network and you can get some sensible answers from that, then that's already a big step forward and quite useful. And the other things that I just highlighted is that the data structure is basically is modeled in the memory structure, or whatever, how the controller accesses it in the memory. So then we talked about what I was mentioning before as well, that basically why you need these differentiable neural computers or computers with neural networks with large pools of memory is that if we talk about regular neural networks, then they also have memory in a sense. The weightings are their memory, but the issue there is that they learn the like broad strokes of the exercise. So if you're dealing with a specific use case, then it doesn't have like a way to store that information if you're trying to like solve problems for that specific use case. That is why they say that the DNCs are good. So capture novel variability as episodic variables in memory. So
I think there is a very, let's say, imagine you have a model, and the model depends on different variables. Then if you always want the network to learn that you have some baseline model and then variables that affect the model, right?
Mm-hmm.
So the question is, how do you achieve that type of model? If you just try to learn, if you try to store all of that information into weights, you have to basically, in my opinion, let's say this memory of of these variables and how you respond to how you understand which variables are present, etc., becomes very hard. While if you have memory, then you can make sometimes one-to-one connections between we have this variable and this affects this model. In my opinion, there is some logical difference there also, where you are able to learn some underlying structures that you place into memory, basically some underlying variables, some underlying where you are in the world, what is happening with this in this current data, and get some information out of it that changes how your model works, but the model is still the same, basically. But once again, might be very physics thinking, but it's like you have the same equation to get from time step x to time step x plus t, but or let's not take time, but let's whatever step from step x to x plus 1. You have the same model, but you have a lot of variables and everything affecting it. And the question is separating those two into kind of two different problems is also something that kind of part of it tries to understand the world and puts that into memory, your understanding, and then you have the model that propagates the state. Which is also a bit on how I imagine the LSTM working, which is why I'm ranting about this thing. But this is, let's say, conceptually in that way superior of how that memory is actual memory, not kind of, once again, a hack inside a neural network.
Yes. Okay. I don't know. I don't think we're going to go through the appendix. So if you want to see the actual how the equations work, there's not anything that difficult to explain here. And I think
it's mostly the same as last time.
Yeah, it's the same last time. So if you want to understand those, I just suggest you try to understand them yourself. Do we have anything else? Do you have any other ideas that came from this too?
No, but we can discuss next time.
Yeah, just wondering, if we go through this abstract again, did it achieve? Just try to did it achieve what it said in the abstract? It's always actually, I think, interesting to read what people promise in their abstract and what they come out of it. I haven't actually done this exercise with this one, but it's just interesting to now look at what we've gone through the article and see what the abstract itself said, which most can be quite the same, but just let's see. So their plan was to introduce a machine learning model that they did, which is called a differentiable neural computer, which consists of a neural network, which can be anything, which they used a long short-term memory one in this time, and that can read and write from an eternal memory matrix. So, which is it does say analogous to random access memory, which is, I agree, but still my main point is that they're talking about instantaneous access, or at least, let's say, the same clock cycle. Everything happens in the same clock cycle. So basically, you don't have this latency or multi-cycle events or whatever. So they actually, something we didn't really talk about, but they actually use two different types of learning methods. So they use supervised learning. So supervised learning is basically you give a neural network its training set with the correct inputs and outputs, and then the neural network learns the correct associations, so to say. And then with supervised learning, they demonstrated that they can do the synthetic questions, answering synthetic questions, where we had like John is playing ball in the garden, where is the ball? And then the neural network understood where is the ball. So this was to emulate reasoning and inference problems in natural language. And I think they had both deduction and inference, which is.
I think it's like deduction and induction, but yeah. I'm not sure if they had induction. I think deduction is theoretically also belongs in the inference. Fuck, I don't remember logic-based bullshit, especially in English. But still, to me, it categorizes under bullshit, so I don't want to read about it either.
And then the second part, they also did reinforcement learning. Do you have a good explanation of what the reinforcement learning is?
You get training signal while the thing is running or working instead of retraining a network.
So it's like
and in supervised learning, you have here is a training and test set, and here are the correct answers and incorrect answers. With reinforcement learning, you aren't able to classify two correct and wrong answers, but you basically try to minimize some kind of a cost or try to play a game very well is usually a reinforcement learning problem.
Yeah, that's what I also want to say. It's usually used for video games. And with the reinforcement learning, they did block puzzles, which yeah. I didn't say which one did they use for.
When where it
the
had to
paths.
predict. Yeah.
That was also the graph, basically the metro underground or the tube. Anyway.
No,
the graph
underground stuff.
Yeah, it was supervised learning. I just haven't highlighted that part. I was just wondering.
Yeah, that's supervised, but the one where it tried to predict the subsequent moves and it had this game, that was supervised learning. Or sorry, that was reinforcement learning.
And so basically, they wanted to demonstrate that the DNCs have the capacity to solve complex structured tasks that are inaccessible to neural networks without external read-write memory. So I don't know if you can fully say this. You can say,
you can say that.
Yeah, you can say that it hasn't been done yet. But
I mean, inaccessible is does a lot of work here.
Yeah, yeah. I mean, that would. I mean, I think for that they would have to prove that that's the case, but they don't do that.
Yeah,
I mean that was the reasoning with why you need basically memory. They talked about it, but they're not really. They can't prove it, right? Or am I wrong?
Yes, and I would say that their architecture is better for solving those tasks that they presented, and that is important result and etc. But it is naive to think that this architecture is the only solution to that thing, because as we described before, memory is a complicated thing. We don't know even how, let's say, like memory storage, and we don't necessarily need a separate, I know, read-write memory like computers do to achieve probably many parts of memory access. And you could even say LSTM does it in some way, in some context, and it does not do the read-write memory. It does a shittier job, and it seems to fundamentally not solve the problem in the same way, but it's still memory, and even neural network weights are in some way memory. So I don't know.
Yeah.
They just don't have a big enough neural network yet.
GPT-4, 5, whatever.
Yes, exactly. I think these problems might be solvable with, once again, more complicated. I don't want to say traditional, but might be with a very different architectural neural network that does not include the external read-writes.
Also, it would be interesting to see what are the shortcomings or what kind of problems it aren't suited well for this kind of neural network.
Yes,
but usually nobody writes about that.
Yeah, part of it we will learn from the next article where they will say we solve these problems.
Yes.
But realistically, I think the training is not very easy to do with these networks. It's something that we have gathered from the previous one, and I think it is also similar with this one. So it is not actually easy to get the training done well, and I think this mentions it here. Yeah, we demonstrate significantly improves. Okay. Compared with differential neural computer and its variants, our memory model has greater capacity and is significantly easier to train. Yep. Yeah. So. Yeah.
So this is the next article we're going to be looking at, so the Conerva machine, published 2 years later now than the last one. This is still by the same guy, Alex Graves. Obviously, he's not the main author anymore. So is it like a corporate? Is it still from DeepMind?
Yes.
Okay, so still from DeepMind, and yeah, this is what we're going to look at. We're still basically on access. An end-to-end trained memory system which quickly adapts to new data and generates samples to like them. So I generate samples. So this is like a copying. What do I get out of this? I haven't read the article, so I'm just going off of this. We present an end-to-end memory system that quickly adapts to new data and generates samples like them. So it's just like a copy machine.
Don't know. I haven't read anything about it. I linked quickly what are the next steps that are going on in the exactly same space. But I think we could take a small break with memory-based stuff and come back to it again.
So what would you want to do, the curriculum learning one?
I think that's a good idea. Or expand horizons a bit, because I think it's a good idea to learn a bit more with other stuff, and then maybe when we come back to this memory-based stuff, we will have a very different perspective.
A survey. Okay, we'll find a specific one we're going to use. Maybe a survey is good. But yeah, so
very good one.
Yeah, so next time anyway, we're going to be talking about a paper on curriculum learning, maybe the one that started it all. I think it was linked in this article, which is let's see. So curriculum 2829. So 2 papers that were linked in the last article are basically just one is called curriculum learning, was in proceedings of the 26th International Conference on Machine Learning in 2009. And the other one is in 2014, Learning to Execute by Zaremba and Sutskever. Anyway, we're gonna look at different ones and see which one seems the best suited for this one. Okay, if you like this, then like and subscribe. Yeah, I guess see you next time.
Share, like, and subscribe. Click on thumbnails or something. I don't know how it works.
Yeah, I'm gonna.